be a good crowd, so we can start. Any questions or comments? Okay. So we should go on with neutrino. What did we learn yesterday? How to say in a nutshell. Someone wants to help me and tell me what we learned yesterday, or you don't want to?
About fermion mass and neutrinos. Majorana neutrinos.
Right, but what did we learn? How would we? What is the?
We learned that neutrino gets its mass. It's Majorana.
No. That's a little, it's close, but a little too much. That we cannot learn because neutrino could be a Dirac particle. We don't know a priori. You see, a priori, I have a neutrino, nu L. It's together with EL, right? So now we go on and we are building a theory of neutrino mass. We want to build it. Actually, it's built nu L, EL. And then this was ER, right? This is our standard model. Of course, if there is no nu R, as we said, then you are right. The only mass possible is Majorana, simply because it can only involve nu L. So the only thing I can write like this. And of course, we have to build it from a symmetric theory. And we started very naively. We said we'll add up just the scalar fields. It's a dimension 5 operator. And there was a little sheet. We said, why don't we build it as a really symmetric operator? Well, we can do that really. This comes from with a little help. I managed to do it. I was helped. We should really use the lepton doublet. There is, of course, phi and the Higgs doublet. So you make a singlet, but it's not Lorentz singlet. So you add another SU2 doublet, Higgs lepton combination, which is a singlet, and this is now Lorentz singlet. Okay, this is SU2 singlet. This is SU2 cross U1 singlet, actually. This checks. This is SU2 cross U1 singlet. This checks. And this together is also Lorentz singlet. Okay. So we build it. And then, of course, since there is only nu L, we are bound to have what is a Majorana mass term. So what we learn, kind of, you know, let's call it a theorem. I don't know if that's maybe too strong of the word, but anyway, if only standard model degrees of freedom the only thing we can have is D equal 5 effective theory. which implies Majorana neutrino mass. Here goes the argument that Weinberg uses a lot in recent years. He's even given some colloquia to ICTP, the most recent one, less than a year ago. He keeps repeating this statement. And 2 years ago, in the 50 years of the standard model, and actually I ended up with a very, very strong fight with him that got resolved. Afterwards, I got invited by him to Austin and we had a long discussion. And I want to tell you where Weinberg is wrong. Because you will hear this argument a lot. This is now how Weinberg says, look, please, this is very important. The next thing he says, look at my operator, okay? He's very proud, this is his operator. So he says, look, you have, once again, what you have, bottom line from up there is this. Because phi has only, after all, he's gonna work in the unitary gauge, which is okay. He's not renormalizing his theory. He just wants to get the physical picture. So he says you get this. We wrote this yesterday. So this is V plus H squared over lambda. This lambda, you know, lambda sometimes, I don't know, sometimes you will see me, I may write lambda nu, or we could even write that this is lambda of lepton number violation. We said yesterday this operator, this violates L. L will be lepton number for us. And it violates by 2 units. So we can also call this scale the scale of the lepton number violation. Okay, sometimes in the literature or the neutrino mass, or sometimes so people would write lambda Weinberg. This is not lambda weak, this is lambda Weinberg, and so on and so forth. So what you get, let's go on. There is, of course, Hermitian conjugate, but that you know, Lagrangian always. So this is we could call it effective Lagrangian for neutrino mass, for neutrino, let's call it. So we get first that m nu, the first piece is m nu, is v squared over lambda. And the next, we learned 3 things, and we said Yukawa nu is, what did we learn, was m nu over v. Yesterday. So from here we can write, and we know that MW, let's give this fundamental relation. We can be very precise if we wish. So V is, what is V? 2 over GMW, so this would be 4 over G squared MW squared over lambda. This is M nu. And Yukawa nu is, what is Yukawa nu? Is G over 2, M nu over MW. So Yukawa nu is hopefully small. Remember, this is where we stopped yesterday. Some number of order 10 to the minus 11 or less. Forget it. This effectively goes to 0 for us. This is kind of sad. So although, you know, Weinberg can say, I have the theory, look, I have it. At the end, I don't know how to verify it because the effective Yukawa is too small. Well, neutrino is Majorana, but there are many other ways of getting Majorana, so I don't have to subscribe to this. What he is right, however, if this is, the theorem is true, if only standard model degrees of freedom, then neutrino will have Majorana mass, whatever model you use. Now let's inspect it a little more. He says, look, from here, I can now compute lambda. So what is lambda? Is 4 over G squared, MW squared over m nu. But m nu is less than 1 electron volt. That's from experiment. Neutrinoless double beta decay. We have to come back and talk about neutrinoless double beta decay. That's going to be an important topic for us. But we also know that neutrino mass has a lower limit. What is the lower limit on neutrino mass? After all, if m nu is 0, then lambda is infinite, right? But lambda is not infinite. M nu is not 0. What is the lower limit on m nu? Who can help me? How do I know the lower limit on m nu? Which is to say, how do I know the neutrino has a mass? We talked about it. Smirnov talked about it, but I will remind you.
Neutrino oscillation.
Neutrino oscillations, right? So where is the number? Well, it comes from atmospheric. I've asked you to know roughly. This is a roughly 10 to the minus 3 eV square, which implies that neutrino mass is bigger than about 1 over 30. I think the number comes 1 over 25 eV, something like this. Cannot be smaller than that. Otherwise, the difference would be smaller than what I'm cited. So this is atmospheric. That's right. Atmospheric, of course, I mean oscillations, as we said. Very good. So we can say that m nu to us, when we make estimates, let's take it some number of the order 1 over 10 electron volt, roughly. Which gives us that lambda g square is about, it's 0.6. It's about a quarter, so I get a little bit, roughly a number of 10. MW is roughly 100. So this will be 10 to the 4. I'm putting everything in GeV. And then this is 10 to the minus 10 in GeV. Let me write it here for you guys to have this. When you write it in GeV, you understand how light neutrino is compared to a proton, say. So what do we get? We have some scale on the order of 10 to the 14, even 10 to the 15 GeV. Look. So here is the Weinberg says, look, the scale is so large that he says, you young people, he now preaches, should not work. On neutrino mass, because there is hopeless. The scale is so large. The scale is hopelessly large. So it's not an urgent subject. It's very strange because he often says that he supports the idea that you should work on strings and so on. Very strange argument. Now, he actually is cheating. He knows that. I mean, he's no fool. He's a great physicist, of course. As great as you can get. So he's cheating here. Now, I want to see whether you are aware where he's cheating. In order to help you, because I claim the opposite, okay? And actually, I'll give you the reasons where the scale not only could be small, but would have to be small. I'll give you a physical reasoning now in the today and tomorrow we will continue with neutrino mass. It's too important to leave it. So we started with lambda effective. Look, let's write it once again. Please, let me write. So it's, to emphasize this, we'll write the way he wrote. I'll write symbolically, if you don't mind. LL phi phi. You understand what I mean by this, right? LL phi phi is this operator. This operator here. We can call this operator effectively LL phi phi. Okay, you appreciate this. Sometimes symbolic notation is very useful because you want to see the protagonist of what you are doing and not the actual detail. So this is how he wrote it. And then we concluded, so now I'm writing lambda W is roughly 10 to the 15 GeV. Where is the cheat here? You see, we can write like this. We can write like this. Let's put some G, some Yukawa G effective, and call lambda G for fun. I mean, this is not a very original thought. So it doesn't, G, let's G stands for Goran, okay? Just though because Goran is making this argument, which is kind of trivial. I could have written like this. He could have written like this. It's just a question of writing, you agree? Where lambda G is lambda Weinberg divided by Yukawa G. Let's forget this effect. You understand now the scale is actually arbitrary. If Yukawa G, so here you have take Yukawa G to be 10 to the -1, say, which is often a small coupling. Now you will get that lambda G is 10 to the 14 GeV. Oh, you are saying, but that's let's write effective because it's really effective. Notice this is a dimension 5 operator. This is like the square of the usual Yukawa. There is something about this that typically Yukawa would have only one scalar, remember, but we have actually two of them. But anyway, now take Yukawa G effective to be 10 to the -5. This is like the electron Yukawa coupling. After all, why should I take it to order 1? I'm talking about the neutrino that lives together with the electron. Now, all of a sudden, lambda G is 10 to the 10 GeV. Well, very big still. This is equal to Yukawa electron. Now take Yukawa G effective to be Yukawa electron square. Because this is quadratic in Higgs. This is very important. Whereas Yukawa E, this corresponds to the term linear in Higgs. Actually, you will see how it happens naturally. You get actually the square, but I'll talk about it later. Over Yukawa E square, which would be 10 to the -10. And now all of a sudden, lambda G would be 10 to the 5 GeV. My God. We are getting close to the LHC physics. You understand that there was a cheat. Message. I'm sorry, please bear with me. There is some interruption. 1 second. Sí. Sí. Sí, tremendo, sí. 1 second, please. The problem of teaching from home, there is a delivery. 1 second. Buongiorno. Sì, grazie. You see what the message is? That when you write an effective theory, you cannot know what the scale is. That you cannot predict, because how can you predict the scale without having a theory? In effective theory, when you have an effective theory, the scale is arbitrary. Sorry, let me write more clearly. Is this clear, please? It should be. And you should be very careful when you read what. Give you an example. Fermi theory. G Fermi, I can write as 1 over lambda Fermi square. And this is how people used to do it. But it's actually, in the standard model, G square over 8 mw square. So the scale is not lambda Fermi, it's the physical scale is this one. This is the physical scale. Of course, G is not very small. G turned out to be 0.6. So MW is about 80 GeV. Whereas it would have been here, roughly lambda Fermi would have been 1 over 300 or something. Sorry, it would have been 300 GeV. For a smaller G, a priori you didn't know, G could have been a much smaller number. Take also this, very interesting, okay, take Newton. So we write G Newton as 1 over m Planck square. And what is m Planck roughly?
Into the 19.
10 to the 19 GeV. So people often tell you that this is the physical scale when gravity gets wrong. This is wrong. Many years ago, Glashow made a trivial statement. He wrote this as G Glashow square over m Glashow. I'm writing this. This is not Warren, this is Glashow. Just to emphasize, if G is small, in other words, at the Planck scale, for sure the gravity will get strong, but it may get strong much earlier depending what this coupling constant is. And there is something which is called the ADD program from extra dimensions, very interesting work of Arkani, Hamed, Dimopoulos, and Wali, where this GG is much smaller than 1 if you have large extra dimensions. This is just an en passant remark. So you see, in effective theory, we really don't know where the physics will take place. The new physics may take place at a much smaller, lower scale. And it's very important that you and I be open-minded and we say, let's wait and let's see what the scale of of this new physics is, assuming that Weinberg is right and there are no new light degrees of freedom, let's take this for granted. After all, the Standard Model is a very successful theory. There are strong indications that there is no new scale, no new states at nearby energy, so it's a reasonable assumption what he's making. The starting point of his analysis is reasonable. The conclusion of Weinberg is not correct. So my point that I was making as a young man, I insist I want to work on neutrino mass. You know, this is very interesting. You see, look. I mean, think about what great physicists do. So what did Weinberg do? What did Glashow and Weinberg do? So you had Fermi theory. This is very important. Fermi theory was effective. But the fathers of the Standard Model, the Glashow, Salam, and Weinberg, what did they do? They said, no, we don't care about the effective theory. We want to build a fundamental theory. That we can use to compute, that works at high energies. For example, effective theory, you cannot use at high energies. You don't know how to compute. This is often called, in modern language, ultraviolet. Ultraviolet means highest energy, ultraviolet completion. We complete this effective theory, okay? Ultraviolet. Which means high energy. Right? Because how do we compute it? Whereas effective Hamiltonian of Fermi is G Fermi current times current, the lambda fundamental from here, or no, it's better to say like this. I'm sorry, it predicts lambda fundamental is some coupling constant G. I'm not writing square roots of 2, some new messenger W mu, and the current plus Hermitian conjugate. This is sorry, J mu bar, because the current carry charges in weak interactions, and G Fermi is just roughly G square over MW square, if you don't care about coefficients, okay? This is the fundamental theory. So in other words, they made their fortune, Glashow, Salam, and Weinberg, asking that this be done. And I want to remind you, this was done in the 60s. In the 60s, experimental scale, energy of the experiment was less than GeV. And yet they built a theory, and MW, however, was 100 GeV, very far. But they courageously built a theory, and the rest is history. Today, the energy of experiment is 10 to the 4 GeV. And we are already building, thinking of the, and it will go immediately to at least an order of magnitude bigger, okay? The China and Europe separately are thinking of building. Okay, this is LHC. This is new. And yet, as I showed you, the scale actually may be easily 10 to the 4, 10 to the 5 GeV, depending what the coupling is, okay? So it's very strange to say that, you know, we young people, you and I know it sounds funny, right? That I want to be in your category, but I also want to make a fortune, and you should. If we could make sense out of a fundament, out of this effective theory, we would be laying groundwork, you see, for future generations. That would be, this is what doing physics means. So it makes sense. And it's essential. It's actually essential to look for a fundamental theory. We have the energies to probe it. Okay, it would be crazy not to try to do it. And this is what you and I want to do a little bit today and tomorrow. And I want to give you a physical motivation, but I want to make sure that you don't have questions here yet. Now, in order to appreciate the scales, we should go back and study the physics of the. So let's step back again. We have to step back when we want to think, reflect on what to do. We said yesterday that if neutrino is Majorana, whether because Weinberg says it or someone else says it, it doesn't matter. That implies delta L equal to, which is neutrino less double beta decay, which was this process. Two neutrons, which is a down quark, decaying into a proton, which is an up quark in our quark picture, giving me two electrons. Two electrons. And we are going here through the famous now neutrino Majorana master. This is what? Let's make sure we get this. Forever, this should be very, very clear to you. So this is W, of course. This is at low energy, so the amplitude we said for neutrino is double beta decay coming from neutrino is proportional to G Fermi square. There is M nu. Let's emphasize Majorana, but we won't always do. And of course, divide it from the propagator of neutrino. P here is of order 100 MeV. This is nuclear physics. Because it's not neutron, this is decaying, as you know, this is happening inside the nucleus. This is some germanium, giving us selenium plus 2 electrons. How would the operator look like? Well, there are two up quarks. Let's write symbolically, two up quarks going out, two electrons going out. This is symbolic, right? I'm not writing chiralities or anything. I'm just writing the way I wrote the Weinberg operator. LL55, just to see the protagonist. And two down quarks got annihilated, they died. So notice I have a, what is this? How many fermions here? 6 fermions. What is the dimension of this operator? Nine. Therefore, this coefficient here, maybe I can write nicer. I could have written, really, what is the dimension of this operator? In other words, the amplitude, I didn't have to write the amplitude. I can write a better notation. I'm sorry. Anyway, you will have my notes. We could write an effective operator. This is really some effective operator. Why don't I just write Lagrangian? We modern language, we write Lagrangian. This is the effective Lagrangian for 0 nu 2, but coming from neutrino. What is the dimension of this coefficient in the front? G Fermi square m nu over p square. You can think immediately. Lagrangian has dimension 4. Therefore, this is 1 over lambda to the 5th power. Which of course it is, because G Fermi has 1 over mw squared. This is precisely 1 lambda 5. Now let me go back where I was before. Let me go back and say the following. Let me go back. Where do I want to go? I want to go here. I said I could call this lambda the lambda lepton vibration. I don't want to do that. I've changed my mind and I do it on purpose like this. Why? Because this operator is not a physical process. This is just some effective way of describing neutrino mass. This is not what you are probing in experiment. This is the physical process of lepton number violation. This is what we should call lambda. This is what I have been claiming for a number of years, emphasizing, and people finally listen more and more, that Weinberg operators is very useful for us to tell us what the expectation is, but it's useless in describing the actual physics, because the physical process is this. Okay, this is the physical process. Of this famous lepton number violation, not Weinberg operator. It's not Weinberg, d equal 5. That was just a master at the end. Yukawa coupling was too small to have any physics. And this is a dimension 9. As is seen manifestly where I wrote. Now you see everything changes when you write like this. I told you yesterday that experiment corresponds today to m nu less than or equal 1 electron volt. We get rid of my Rana. So in other words, the experimental number 1 over lambda lepton number violation is roughly, just for you to get the numbers, G Fermi square, m nu over p square. Well, it's maybe even, let's be conservative, because they are saying that it's number which is close to 10 to the minus 1 electron volt. I was very, let's imagine it's even smaller. Okay, this is anyway next generation, which is now in process. There are a number of experiments going on. Let's include them to get a feeling, because we are saying, suppose there is a discovery. G Fermi, remember, is 10 to the minus 5, GeV to the minus 2. P is 100 MeV, which is 10 to the minus 1 GeV. So what do I have? I will have 10 to the minus 10. M nu, let's put 10 to the minus 10. The sensitivity of experiment divided by 10 to the minus 2. And the is GeV to the minus 5. So what do I get? That lambda lepton number violation is roughly, no, to the 5th power. Why did I write lambda? This is to the 5th power. Nobody's correcting me, please. Make sure to the 5th power is I get roughly 10 to the 18 GeV to the 5. I'm now doing the same thing that Weinberg did. I didn't put a small coefficient. Remember, if I put a small coefficient, I get even a smaller scale. I'm just pretending the coefficient is over 1. Mr. Weinberg says, I will write this as 1 over lambda, and the scale is large. Now look at the reasoning that we are using here, please. If you put a small coefficient, you get a smaller scale, but notice what we got. If I take this process as a measure of lepton number violation and not the Weinberg operator, I get, this is experimental sensitivity, which we used for neutrino mass above. I will get that lambda lepton number violation is roughly about 3 TeV. This is what is being probed in experiment. If I'm right, and where could I go wrong? This is the only experiment seriously probing lepton number violation. There is also the collider physics. I'll come back to that at low energies. The neutrino is double beta decay. There are tens of experiments. The whole world is looking for this. The experiments are called Quore. I like to say that people are, this is some cryptogenic underground acronym. I don't know, and so on, okay? This means heart in English. So I like to say people are pouring their heart into it. So this is Quore experiment. These are experiments. There is Gerda, Majorana, EXO. There are, these are the guys that are probing this. Not only even if you're just naive the way Weinberg was, not only the scale is not terribly large, this is tailor-made for LHC. I hope you are paying attention here, because what I'm showing you is actually contrary to what is being claimed often in the literature and in the conferences. The Majorana picture of neutrino may be actually probing a scale which is extraordinarily close to us. And this is what I claim now, that the study of the origin, and it's not just the origin, and nature, we need to know whether neutrino is Majorana or not, and nature of mu is urgent. It would be crazy not to work on this, that tomorrow we make history. This is the only door that we truly have to beyond the standard model physics. The only incompleteness of the standard model is in neutrino mass. You may hear, of course, of other interesting issues in today's physics, like dark matter and so on, but the standard model has nothing to do with that. This is not incompleteness of the standard model. Standard model had nothing in it to be the theory of dark matter, never pretended, but it is a theory of neutrino because it's a theory of weak interactions. I hope this is very important. And let me tell you how we may actually be knowing that we have to work on this. Imagine you see neutrino is double beta decay tomorrow. You, me, are. Imagine they see. Okay, you, they see. And they tell us. Usually they tell you, by the way, people that give talks, and be very careful when you go to seminars, okay? You can tell them that Goran taught you that what they are saying is nonsense. When people say that they notice neutrino is double beta, they say they see that they prove that neutrino is Majorana. They say we are measuring. They say, equivalently, they are saying we are measuring neutrino Majorana mass. This is the claim of experimentalists very often, even theorists, unfortunately. Why, they say, but look, they are saying. After all, they say, look, you can go, you object to that, but they say, look at the lecture of April 7, 2001. Look at it here. It's going through neutrino Majorana mass. This is what Goran wrote. Now tell me, I need to know that you are there. You see, I'm giving, this is a very important lecture for us, all of us. And you should be on the highest possible alert. Tell me, what is the chirality of the electron in this process? I'm asking a question. Chirality of electron. Polarization, we often say. Who can tell me, please? I need to know that you are there. It's not easy to teach without seeing your audience. You know this? I should have the right to wake you up at 4 o'clock in the morning. You know, I wish I had some alarm. I'd wake you up and say, you know, what is the, before you even open your eyes, what is the chirality of the electron in this process? I need someone to tell me. This is the most essential weak interaction process. It's beta decay twice. All of the physics of today is about this.
He's left-handed.
Left-handed. Only left-handed. That you know with fantastic precision. This is very, very important. I cannot overemphasize this. This is what people claim. However, this is completely wrong. It cannot be more wrong. In other words, 0 nu 2 beta in general has nothing to do with neutrino mass. In general, a priori, no connection. In general. This is the statement. This is true. Why? Just think of this. Okay, why? Imagine that at least one of the electrons that comes out is right-handed. You measure its polarization and it's right-handed. In other words, I go back into this process, or I do it here. I do it here. So what is it? What I really see, what an experimentalist see, they don't see what is going on. What they see is this: 2 neutrons, 2 neutrons, 2 protons, 2 protons, 2 electrons. No, I should draw this nicer. I'm sorry. I apologize. And I was using quarks anyway. I'm doing this really. I get 2 down quarks entering, or put in the bracket at least 2 neutrons coming out. What's coming out? That's the only thing they see. 2 protons, they see. This is in the nuclear physics, and 2 electrons. This is experiment. 0 nu 2 beta experiment. Experimentally should not tell us. A low energy experiment cannot see what is happening. All they see here, a black box. Now, imagine. Now you measure E chirality, which is polarization. Electron is very light, and you are basically this exchange momentum was 100 MeV. It's almost massless. It's not easy to measure polarization, but in principle you will when you have enough data. You measure the helicity, measure electromagnetic, and imagine and look here. If E is ER, at least one of them. If just one of them is ER, notice it does not come from neutrino Majorana mass, period. Why? Because in the neutrino Majorana mass, you told me, both of them come left-handed. They must be left-handed because W is, let's emphasize it. We can even remind ourselves that W is left-handed. The crucial thing here is that the fundamental weak interaction Lagrangian that we write like this, J mu, W mu, nu L bar, gamma mu EL. You can even put here L if you wish to remind you that the W of the standard model, okay, W is really some kind of funny guy that couples only to left-handed current. This is very important. The electron is left-handed. Both electrons must be left-handed. Therefore, if they do the experiment and at least one of that, that means that 0 nu 2 beta comes from new physics. Nothing to do with neutrino mass, some new physics. Not directly neutrino mass. That neutrino may be Majorana, be massive. Well, maybe, yes, but it's not coming from neutrino mass directly. It cannot be because they would be left-handed. But we also know that lambda of what I call lepton ovulation, which is lambda of this new physics, which I can call lambda and P, must be some number. I estimated between 1 and 10 TeV. I said roughly 3, but that was sort of coefficient I took to be 1. And this is very exciting, okay, which is testable. Maybe at LHC, but surely at next collider, which we are getting ready for. So we have to understand, you and I now have to spend a little time thinking about the fundamental theory of neutrino mass. But that we never do before the break. We have to take a little break, you and I. I want to know whether you have a question or not here, or you prefer to wait for the... Okay. You're not giving a question. I have 11:57 and I write round numbers. Let's meet at 12:05. let's take a break of 7-8 minutes. And I'm still pausing here in case there is something urgent. If not, at 12:05 we continue with the discussion. I will. When I come back, I would like to speak about the going into the theory. Okay. Any questions, please, on this? So that we can move on.
Yes, just one clarification.
Please.
So to show that the neutrino mass is Majorana, if we see the neutrino as double beta decay, we have to make sure that the chirality of the electron is left-handed.
So
the only
right. So very good question, you see. So what did I say? Okay, let's try to have a summary of this beautiful, important experiment. Very good. First, if at least one of the electron is right-handed, one is at least one. I don't need both. What I learned, it's not neutrino mass. You agree? We agree here. If both electrons are EL, both, what then? This is a very important question. This is what you're asking me. Am I right?
yes.
Right. Is it coming from neutrino Majorana mass? Question. Answer. Suggestive. But not necessary. Whereas I can know that it's not coming from neutrino mass. This is a very, very, very fundamental question, and I'll try to say a little more. Not necessary. There has not been a clear analysis of this at all. I'm writing a paper on this in collaboration with Dwali, Mayetza, and Teo. Mayetza and Teo, my younger collaborator, Dwali, my old collaborator colleague in LMU in Munich. We are writing a paper on this. This is being written. Being elaborated. And the answer is not necessary. It is suggestive. We give examples in which even if both are left-handed, you could still have, in other words, still possible, not so natural, but still possible to have new physics. Cause 0 nu 2, but still possible. This is very interesting. So more is needed. And what is needed in this particular situation, you see, you will need. So what is needed, more is needed. And that's what is needed to the different isotopes, different nuclear decays. Different isotopes, one says. Why? Because you have to distinguish whether the process is coming from a light particle like neutrino or from a heavy particle. So you have to entangle. In order to entangle, disentangle. Disentangle whether it is neutrino or some new physics, which is whether it is light source, you read neutrino, or heavy source. And that will not be easy, but it can be done in principle with a lot of hard work. And we go now into some ugly analysis of nuclear physics. I don't want to bug you with that, but I want to tell you, when you listen to talks in the future, just be careful about people when they claim a discovery of neutrino mass. That will be wrong. First, they have to do the polarization if they want to convince us. They have to get both of them left-handed, and then they have to do even more and compare with other isotopes, okay, and that's gonna take a long time. Meanwhile, we should be ready to think, what if it comes to right-handing? We should try to understand what kind of new physics am I talking about? Remember why I'm talking here. There is a very important message. Why do I keep talking? Why new physics? Why do I keep stressing new physics? Because what we said, that if you have a neutrino Majorana mass that comes in the standard model picture, remember what we said, it comes with as a higher dimensional operator. This is the scale of new physics. In the standard model, why? In the standard model, m nu Majorana is 0, which is equivalent. Lambda is infinite. There is no neutrino mass. Therefore, even just to think of neutrino Majorana particle, you need new physics. So new physics is always there. It's always there. The only question is, what is the lambda of new physics? Which I call lambda of L number violation. What is that? Well, that's what you and I want to probe. And in order to speak about it, we need a theory. Doesn't make sense to keep using generic words. So what we want to do next, we want to talk about the theory of neutrino mass. There are hundreds of models that people wrote on neutrino mass, and as I'm speaking now, someone is sending a paper to our archive with yet one new model. Okay, we are bombarded. There is a plague of models, some of them senseless, some of them having sense, some of them having some rigor, most of them not. In order to understand why I want to speak of a fundamental theory, let's step back now. Let's step back once again. And let's go back to the standard model. Standard model once again. And origin of mass. Let's talk about it. The characteristic of the standard model, as you know, there is a gauge group. Just to remind you. So here I'm just going to remind you of things, but I'll tell you something else. So if you wish, this you will not find in any book. If you wish to, and it should be in all the books in the world. And that's the following. What was the crux of the standard model? Remember what we said. Is this a symmetry? This is how standard model looks like. So now notice, to get a mass, so from here you would have that the fermion mass is 0. So the next step is add the Higgs. And that's the famous doublet. And now, of course, you can write Yukawa interaction, which is typical U bar d bar L, Yukawa d phi dr, and so on. We wrote it many times, plus other terms. Phi unitary is 0 v plus h. And from here, we find out that m fermion, every fermion that has a mass. So fermion is up, down, an electron here in this case, times v. And Yukawa fermion is m fermion over v. This is what we have, right? Where this is our Higgs. Now you see, in order to have a Yukawa coupling, the crucial thing was maximal parity violation. This is how you could build the theory of mass. Now imagine, so in other words, the simplicity and beauty. So you see what happened with just one doublet. All masses. By this I mean W, Z, up, down, electron. We have more generations, I don't care. All masses except neutrino. This is very important for you and I. And everything predicted, you see, all the masses are simply proportional to fermion mass. The theory can be easily tested. This is a beautiful, simple, predictive theory. This is what we love about the Standard Model. To understand the point, imagine now a world, a fictitious world of parity conservation. Imagine that Li and Yang had been wrong. Imagine Madame Wu doing an experiment and she finds that parity is beautifully conserved. In other words, imagine the world which is left-right symmetric, FL going to FR symmetric. How would it look? This is, of course, not true world, not real world. Please don't get confused. But this is very important, okay? I want you to pay attention here for a little while. Because if you understand this, you will understand really the essence of the Standard Model. How would the gauge group is still the same. Imagine there is just W and Z. I want a minimal gauge group. 1961, I'm Mr. Gleshow. So I'm going back to 1961. And Gleshow wants to build a theory. And of course, the minimal theory is SU2 cross U1. He cannot call it SU2L. He may write SU2 cross hypercharge, but it's not L now because the world is left-right symmetric. So how do the fermions look like that we call matter? How would he choose it now? There is UDL. W interacts with left-handed fermions, but also in a symmetric world with right-handed fermions. So how should I write the right-handed up and down quark?
It should also be a doublet, right?
Yes, yes, you see. It's a very interesting thing to try to, when you are understanding physics, trying sometimes to think of different worlds to understand how you would be building the theory, because when you read in the books, you don't really understand the process. Okay, in this world, so let's just talk about quarks. It's left-right symmetric by definition, QL, QR. Now notice if I want to write what is so-called Yukawa interaction, I can write a mass term like this. Let me put capital M to emphasize. This is now invariant because the world is left-right symmetric. Why? Because QL and R transform in the same manner. They are doublets, as you told me. So this is obviously invariant. And because they are symmetric, they have the same hypercharge. In this world. So this is invariant. You see what we get. Fermions now have a mass, and we predict that, of course, mass is the same. We predict that M up is equal to M down. And if there are more, for more generation, that means M strange equal to M charm, M top equal to M bottom. That's very wrong, completely wrong. And M is a gauge invariant number, so you would expect it to be much bigger. The natural expectation is, why in the world this is not much bigger than MW? It's not coming from some standard model scale. It's just a God-given number there. This is kind of natural, but okay, natural may not be true. So you have a sort of interesting puzzle. Why are fermions so light? Here in the theory, first, the predictions are wrong. This is 1. And 2, why are all the fermion masses on the order of MW or much smaller? That remains a question. Well, anyway, now we have to split the masses. We have to do something. Also, at this point, MW is equal MZ equals 0 without the Higgs. Now, what Higgs should I take? The doublet will do me no good. First thing I notice here, doublet, no good at all. This is very important. I cannot write QL bar phi QR, you agree? Because this would transform into QL bar, U dagger, U, phi, and then again U, QR. This is 1. This is not good. Why does it do this thing? This is no good. Not invariant. So you see, the beautiful thing in the standard model that you could get all the masses from a doublet. Here it's completely wrong. Simply the doublet is the last thing you would think the doublet. Okay. So A, tri-bubble, not good. What next? A, B, C. If it's not a doublet, can you tell me from the quantum numbers here? I need, in other words, what I'm asking you, I need my Yukawa coupling is QL bar, MQR I wrote. Now I need some Higgs, which would be QL, some Yukawa, some Higgs. Let me not call it phi. QR. What is the quantum number of H? See, QL, QR, QL, and R are doublets. That we call 2. What is 2 times 2 in SU2? You can tell me 4. What is 4?
3 plus 1.
Yes, you can have a singlet or a triplet. Of course, you can have a singlet that in quantum mechanics, when we did quantum mechanics, doublet, that would be spin equals 0. And this would be a triplet. Spin 1. In other words, what we are saying that H is, let me call it T, a triplet. It's what we call a vector. And it has 0 hypercharge. Because QL and QR have the same hypercharge, QL bar QR. So it's a triplet that we studied. Remember, what does it break? The triplet breaks SU2 down to the wave of the triplet, which is called vector. What did we find out when we studied it?
SO2.
Sorry?
SO2.
Right, or U1 we can say. Thank you. So you see, I don't even break the, in other words, SU2. So what I'm saying is, it's not even complete now. I'm really in trouble. Breaks down into U1 cross U1. This is not the symmetry of our world. So we need even more Higgses. I mean, this is really sort of ugly, okay? So we will need more Higgs, maybe a doublet. Now notice the celebrated paper of Weinberg would never have been written. Weinberg would have gone crazy here thinking, and now he's writing, okay. So Yukawa is QL bar. And this is a singlet, you see, it's a singlet. That's why we got the same mass. Plus, let's call it Yukawa triplet times QR. And remember, triplet we can write as a joint. In other words, triplet, we love to write that is U triplet U dagger. Then, of course, it's invariant. This is how we've learned to our love that, and that means that the vacuum expectation value, remember, we can always diagonalize a Hermitian T is T dagger, trace T0. This is our famous adjoint. So this is some wave, let's call it VT, in this direction, in the Cartan direction. This is what we found out. So in other words, now M up is M plus Yukawa T times the wave of this guy. M down is M minus Yukawa T. We managed to split them. But notice that Yukawa couplings now, however, Yukawa coupling is not M fermion over VT. It's a very now ugly formula. Instead, it gets ugly. I don't even want to bug you. Very hard to make predictions. Also, we have too much U1. This is equivalent to say that the mass of the Z boson is 0. We have two massless U1 cross U1, MZ 0 and MA 0. MA 0, it's good, but I don't have to have two massless gauge boson. And I just said, need more Higgs. And that means we lose all connection or masses and Yukawa. No predictions now. And it's really ugly and massive. Why would you write that model? You will be discouraged. I mean, even Weinberg is apologetic. He doesn't know that the theory will be renormalizable. He says, look, I'm going to try. And why did he try to do that? It's because of the simplicity, of the elegance, of the clarity of the predictivity. Then, of course, you are tempted to go through this exercise. So this is a disaster. So in other words, parity conserving world, P world, is extremely ugly. We should be happy. You know, there is the thing, why in the world parity is broken? Well, because then I can have a beautiful theory. Whereas the P breaking world, maximal, is actually beautifully predicted. It looked ugly. But we predict m nu is 0. That's no good. Simply wrong. So we need this maximal parity violation. We really need it. But then he gave us this bad thing. Because you see, again a but in the P world, look what will happen in the P world. How does the leptonic sector look like? Nu L. How would the right-handed sector look like? Who's going to help me? You help me with quarks?
It will also be a doublet. with
Yes, nu ER. Notice what happens in the P world. Neutrino is massive. It's just like the electron. If you give the electron mass, you're going to give a neutrino mass. You have a complete nu E analogy. Now there is no asymmetry between them. So in a P world, we have a beautiful prediction of neutrino mass. So in conclusion, look what happened to us. First, we need maximal parity violation for M electron, M up, M down. Two, need P conservation for M nu. In other words, at the same time, I need a symmetry and I need to break it. Remember what I told you, that when Nambu introduces spontaneous symmetry breaking, C.N. Yang is giving him a hard time, saying, look, you don't understand, the symmetry is either broken or not broken, but actually you and I know something special, what Yang didn't know. He completely missed on gauge series. This great physicist somehow, I don't know what bugged him. You couldn't get him excited. I'll tell you an interesting story later about Li and Yang. But what Coleman says, you see, when you need to break the symmetry and you also need the symmetry, what should you do? You need spontaneous symmetry break. As Coleman called it, hidden symmetry. In other words, what I'm saying, you see that if you want to understanding neutrino mass, it's very, very suggestive that parity violation spontaneous. This is from the modern reasoning that you and I would use today. The beauty of the thing is actually that the idea preceded its logical, okay? In 1974 and 75, this is precisely what was done. What was done is the left-right symmetric theory was being built. Left-right symmetric theory with parity violation spontaneous. It was there from the very beginning, the theory of neutrino mass. So how do you break? So now let's study that. how do I break parity violation in the spontaneous symmetry breaking of left-right? Let's show how to do this. Look, what I mean is the following. I have to start, in other words. So we are building. We are building a left-right symmetric theory. We are motivated today from neutrino mass, but by the way, the motivation came originally from the attempt that some of us had, and that is to try to understand deeper the origin of parity violation. Forget neutrino now. Imagine that you are saying, I believe that the world deep down. By the way, this is very interesting. If you look at the Lee-Yang original paper, the parity violation paper, it has 4 pages, 56. And they are suggesting 3 pages talk about parity violation. Page 4, they say that they believe that at fundamental level, when a new theory, when a deeper theory is found at some fundamental theory, P should be a good symmetry. After all, P is the symmetry between the left and right. Is the first symmetry you see as a child. So somehow Lee and Yang say, we believe that this fundamental symmetry will be restored when you have a more fundamental theory. Today we are suggesting parity is broken. Okay, so this is kind of Lee-Yang dream. It's realized in this theory that I want to build it. How should you build it? Well, you use Nike approach. Nike says just do it. So let's use the just do it approach. Once you get an idea, it's not that hard. It's getting an idea. And they, of course, 1956, there are no gauge series and so on. And they wouldn't work on gauge series. Well, T.D. Lee changed his mind and later on he started. Also, what happens to them, they got recognized as the breakers of parity. They got a Nobel Prize a year later. Their whole career was made on breaking parity. They forgot this, by the way. This is very interesting. Or at least pretended to forget, to remember this. I think they genuinely forgot. But you can never be sure. I tell you why I think, because actually T.D. Lee told me this personally, but I'll tell you later. So how would you build the left-right symmetric theory? So let's just build it. That means that matter must be left-right symmetric. It must look like this. As I said, this is the only way from the point of view of our fermions that it make it left-right symmetric. So what does it imply? What should be the gauge group be? It cannot be standard model gauge group. That's ruled out. In the standard model, parity is broken. Who's going to help me? We'll just do this and then we'll stop. We won't talk very much about the theory. I don't want to bug you. This is not the standard model. I just want to give you the essence later on, how it becomes a theory of neutrino mass and how it leads to something which is called the seesaw mechanism. You have to know this is sort of what majority of people is working on, the seesaw mechanism. So I have to tell you a few words. But tell me, what should the group be now? Any ideas?
ACC?
Well, I have left and right words. I took doublets. When I take doublet, it must be some kind of SU2. Look, the standard model was SU2L. In the standard model, only left-handed doublets have weak interaction. But in this theory, also right-handed guys have weak interaction. Well, not really, not the weak interactions we measure, something much weaker.
SU2
Because obviously,
SU2.
sorry?
SU2 cross SU2.
Yes. This is inevitable. The minimal theory. And you could say, oh, it would be nice to get rid of hypercharge, but it turns out that you cannot do that. Why? Because if you don't have hypercharge, if you just take, well, let me say it here, if you just take SU2 cross SU2, if you try this, because you could say, oh, there is inside U1, inside UR. No, unfortunately, Q electromagnetic would then be T3L plus T3R. And that would mean eigenvalues either plus half or minus a half. Because T3 has eigenvalues plus half or minus a half. This is wrong. This cannot be. So this is not enough. Let me just what I need, the minimal G left right is SU2L, just as in the standard model, times SU2R times cross U1. So what it means, in the standard model Q electromagnetic, this is the last thing I will write, was T3, but the world must be left-right symmetric, we are just saying. So it must be T3L plus T3R. If it is T3 on the left-handed fermions, that's a definition of left-right symmetry. So in other words, what I'm saying here, that there is a symmetry between left and right, which I call parity, when left goes to right. So this is because of parity. In this theory, parity is a good symmetry. This is a left-right symmetric theory, obviously. Plus some new generator, let's call it hypercharge prime. I don't want to call it hypercharge. I should call it hypercharge prime. You see, the standard model would be, the standard model hypercharge over 2 would be T3R plus hypercharge prime over 2. I have a question for you, please. Compute Y prime. Compute it for left-handed and right-handed fermions, please. This is a nice little exercise so that we tomorrow will discover something very interesting. It will take you only a few minutes. You know the charges, you know T3. You know T3 because the guys are doublets. So T3L, of course, is going to be Pauli matrix over 2. But T3R will also be Pauli matrix over 2. Only T3L acting on left-handed fermions is Pauli matrix over 2 left-handed fermions. T3L acting on right-handed fermions is 0. T3R acting on left-handed fermions is 0. T3R acting on right-handed fermions is Pauli matrix over 2. Okay.